Today we're going to talk about operational amplifiers, which are often just called OpAmps. Now, OpAmps are not analog circuit devices. You need to understand that right up front. OpAmps are digital circuit devices. It involves some understanding of transistors and diodes and things like that. The operation of an operational amplifier in this class is only going to be related to its outputs versus its inputs. So what we're doing is we're taking a black box approach. We're calling the operational amplifier itself a black box, and we're looking at inputs versus outputs, and that is somewhat linear. And we'll talk about those details later. But anyway, the point is a detailed analysis of an operational amplifier circuit requires an understanding of electronic devices that are beyond the scope of this class. So as long as we take a black box approach to this, then we can use our analog circuit techniques to figure out how it works as far as terminal behavior goes. All right, so what does an operational amplifier look like? Let's begin with that. Operational amplifier is an integrated circuit. It comes in a lot of different shapes. You can buy chips that have 4 operational amplifiers or 2 operational amplifiers or 1 operational amplifier. This one here is a 741 chip, and it has 8 pins, and it's got 1 operational amplifier inside of it. And you'll notice the chip, it's got 4 pins on each side, and it usually fits down into a socket. But the pins have different purposes, and you need to know how the pins are numbered here. So if you look on the top from above of each one of these circuits, you'll see there's some kind of indicator as to which way to orient the chip itself. If it's got a circle, you put that circle in the upper left-hand corner. If it's got a little divot, then you turn it so that that's at the top. So if the chip looks like this, then you turn the little divot towards the top. Or if it looks like this, you put the little circle over there. Now, if you orient the chip that way, then the pins are numbered like this. 1, 2, 3, 4, 5, 6, 7, and 8. And the pins are on the sides here. And the same here. All right, now these pins have different purposes, like I said. For our purposes in this class, some of the pins matter and some of the pins don't matter. For example, pins 1 and 5 are the offset null pins. Now, if you were actually going to build one of these circuits, then these pins may matter. The function of these pins may matter. But for the purposes of solving a circuit in this class, those pins aren't going to play a role. So we'll just say that these are no concern. Also, pin 8. Pin 8 has no connection. Why did they put an electronic device in a container like this if some of the pins aren't connected? And the answer very likely is because this packaging is used for multiple devices, and they just happen to put an op-amp in this one, and the 8th pin is not needed. So there's no connection there, so that means that's not going to be a concern for us either. Now the 4 and 7 pins, those are supply voltages. V plus and V minus, sometimes these will be VCC. V plus VCC or minus VCC. Now, what these are the voltages that power the device that's inside this package. So it's kind of like the plug you plug into the wall to turn something on. Before you can even flip the switch or make the device operate, you have to plug it in. Operational amplifiers are like that. You have to plug them in, and this is how you plug them in. You add the supply voltages on pins 4 and 7 for this chip. Remember, this chip is 741. Chip. Okay, pins 2 and 3, those are the inputs. So you have 2 input pins for an operational amplifier. Pin 2 is called the inverting input, while pin 3 is the non-inverting input. Sometimes if you're drawing a schematic, which we haven't done yet, by the way, if you're drawing a schematic of a 741 or a operational amplifier, pin number 2, the inverting input, is shown as a negative sign, and the non-inverting input is shown as a positive sign. Okay, that just leaves pin number 6, and pin number 6 is the output. So we've got 2 inputs and 1 output. That's the pinout for an operational amplifier. If we draw an operational amplifier schematically, symbolically, it looks like this. It's a triangle. The output goes this way. So this is the output. And then these are the 2 inputs. One is the non-inverting, the other is the inverting. And they're drawn with a plus minus this way, but that doesn't always apply. Those could be switched. So there's no standard for that. So this is non-inverting input, and this is the inverting input. This device needs supply voltages. So those are usually drawn this way, off to the sides, like this. A V plus and a V minus. The specifications for a specific operational amplifier will tell you what these inputs need to be, or a range of values for the inputs. It may also give you a range of inputs and outputs and gains and things like that, and we'll talk more about that in just a minute. Now, in this configuration, this amplifier will do what an amplifier does. It will amplify something. So the output is a gain, has a gain that is larger than the inputs typically. And the output is proportional to what the difference is here. So this, if we have some voltage on the non-inverting input and another voltage on the inverting input, then whatever that difference in voltage is, then that's going to be the output over here multiplied by the gain. So if we say this is V output, and this is, let's call this VP, the P will go with a positive, so it's the non-inverting input, and Vn is the inverting input, so the N stands for negative in this case. Then the output over here is related to the difference between these two. And the amplifier itself has some gain, and let's say that gain is A. So A represents a number that tells us how much greater the output is than the difference of the inputs. So the output is going to be equal to A times VP minus Vn, like that. Now, if you ran, let's say you take the inverting input here and you ran it straight to ground. So looks like this. You run that straight to ground. And then you have some VP in there. Then the output here is going to be V output is equal to A times VP minus Vn, but Vn is going to be 0, so it's just VP. Now, if you did that on the inverting side, so let's say we'd have this situation where this is the output, and now we've run this straight to ground, and we've still got V sub n, this plus minus inputs there. Okay, I made a mistake there. Let me start over. The output in this case is going to equal, once again, A times the difference, VP minus Vn. But VP is 0 minus Vn, so the answer is minus AVN. So the output is inverted. That negative sign means that it's inverted. So if we have a positive value for Vn, we'll get a negative value on the output. If we have a negative value for Vn, then we'll get a positive value on the output. Okay, now what we're talking about here is the linear range of an operational amplifier. There are limitations to this. Let me try to explain that. Now, this A value can be large, can be very large. And the problem is, if it's very large, then it's possible that the output voltage is much bigger than either of the input voltages. However, the output voltage can't just create energy out of nothing. So where does this energy come from? Well, it comes from the supply voltages here. The problem is that depending upon what this A value is, it may be that the output is bigger than even the supply voltages. The limitation is this, that V output is going to be equal to A times Vp minus Vn, as long as it's not bigger than the supply voltages. So it's going to be this if a Vp minus Vn, that's the output, is between your V minus and V plus. So greater than or equal to. In other words, as long as the output is somewhere between your supply voltages, then this is going to be the output. Okay, but if it's bigger than that, if the output should be bigger, then we've got this bracketed case here. It should be plus V, or V plus, if the output is greater than V plus, or it's going to be minus V, and that's plus, if the output is less than V minus. Okay? So when we're talking about this right here, this is saying as long as the output is between V plus and V minus, that's your supply voltages, then you're going to get this linear output. However, if it's bigger or less than the supply voltages, if it's outside this range, then you're just going to get out the supply voltage. And that's all you can get out. In other words, the maximum amount of voltage that you can get out is no more than the voltage you put in. So it has to be that, or else the op-amp would be creating energy out of nothing, and it doesn't do that. So let's take this right here and graph it so that you can kind of see what I'm talking about. We'll put Vp minus Vn on this axis. So this is the difference between the inputs. And then we'll put the output on this axis there. Okay, so this is inputs and this is outputs. Well, there is a range, a linear range here, over which the operational amplifier will behave as expected. That's the A Vp minus Vn range. So if we were to look at what this range consists of, this is minus V plus, that's the supply voltage, over A, and this would be plus V plus over A. So there's the range between V plus and V minus over which it behaves linearly. And the output then, at its maximum here, if you had that as your input, then the output is going to be V plus, and down here, V minus. Okay. Now, outside that range, let's say your input is over on this side, the maximum you're going to get out is this, or the minimum you're going to get out is this. So this represents a saturation that can occur. So it behaves linearly within this range, but if your output should be bigger than V plus, then it saturates. So this is positive saturation, and this down here is negative saturation. And of course, in the middle between those two, that's the linear portion. So once again, your output is going to be this, unless this turns out to be outside the range of V plus and V minus. Okay, well, what does that mean? That means if you go below V minus, then your output is just V minus. But if you go above V plus, then your output is just V plus. And that's what this shows right here. If your output should be more than V plus according to this equation right here, if you computed it and it turned out that the output's supposed to be more than V plus, then you never get out more than V plus. You just get out the positive saturation value of V plus. And vice versa, if it's less, you get out the negative saturation value for V minus. In other words, you cannot get out of an operational amplifier more than you put in. Now, the A value that we talked about, that's the gain of the operational amplifier. This is called the open loop gain. And typically, this is going to have a value of 10 to the 5th to 10 to the 8th. An idealized case would have a very large or infinite open loop gain. Now there is some input resistance, let's call that R sub I, that typically has a range of 10 to the 5th to 10 to the 13th ohms. But an idealized input resistance is also going to be very large, so we'll idealize it as saying that it's infinite. Now there is an output resistance as well, and typically that has values between 10 and 100 ohms. Well, idealized, we would want that value to be very small, so idealized, we'll call that as 0. Now you could also add to this supply voltages, so VCC values can be anywhere between 5 to 24 volts, and idealized, you don't have those. You don't have to worry about that saturation for an idealized case, although you will. Now, having said all of that, so let me show you how to model an operational amplifier. All right, this is how. What we have here is an input resistor. This V sub D is Vp minus Vn. All right. Then this is a controlled source, a controlled voltage source, and it's controlled by this voltage Vd over here. So Vd multiplied by A, that's the open loop gain, is how much gain you have on the output side. This is the output resistance. So what we've got here, if I draw some dashed lines here, this is the triangle right there that represents the OpAmp. So what's inside the OpAmp can be modeled this way. So you can see here the output is going to be equal to the difference between the inputs multiplied by the open loop gain here. Now hopefully all of this will make sense when we start actually using an operational amplifier, and you can see how to solve those circuits. So now let me introduce the first real operational amplifier circuit that you will encounter. All right, so here we've got a simple operational amplifier. You'll notice the non-inverting input is going straight to ground. The inverting input is going over here through a resistor that is connected to the source. So this has some voltage, V sub S, and this resistor is R sub S, so this is the resistor that's closest to the supply over here. Now we're not finished with this just yet, because you've already kind of seen what the output would be for this one right here. You've already seen that right here when we did this. You know that the output is going to be a Vp. But the real usefulness of an operational amplifier comes in when you supply it with feedback. When you take the output over on this side and run it through a feedback resistor and bring it back into the input on this side. So this is R sub F, the feedback resistor. Now this is a type of amplifier called an inverting amplifier. And you may have noticed that the input is going into the inverting side, and it's an inverting OpAmp. It's one of the most basic OpAmps that you will encounter. Now, in order to work this kind of problem and to solve this circuit, what you're really trying to do is find the output in terms of the inputs. So if you could write an equation that V output is equal to something multiplied by the input, and in this case the input is V sub S, that's the input voltage, and figure out what goes in this square bracket right here, then you've solved the problem. Now we will actually solve this a couple of ways. One way is that we will use the modeled version of an OpAmp. In other words, we will use this to figure out what the output is, and we will rely upon our knowledge of the way dependent sources work and voltages and so forth. And we'll figure out what the output is. The other way is what is called ideal OpAmp constraints. Now the idealized case are these things right here. You were probably wondering why I was writing those down. If we make these idealized assumptions, then we can come up with what are called the ideal op-amp constraints, which makes solving one of these problems really, really easy. So here are the idealized op-amp constraints. The idealized op-amp constraints are these. Assume that Vp is equal to Vn. In other words, whatever the voltage going into the positive side, it's equal to the voltage on the negative side. Okay, just make that assumption. Now you might say, well, that makes no sense. Well, these are idealized cases, and we are assuming an open loop gain of infinity, and this sort of just falls out as a result of that. The second idealized op-amp constraint is that any current that happens to be going in on the non-inverting side is equal to the same current that's going in on the inverting side, and those are both equal to 0. In other words, we've got no currents going in here. So there's no current going into the inverting input or the non-inverting input. Absolutely none. Now, you'll notice that Vp equals Vn, but that's not necessarily equal to 0. They're just equal to each other. But in this case, the currents going into the non-inverting and the inverting side is equal to 0. If we make these two assumptions, called the ideal op-amp constraints, then we'll be able to solve this circuit pretty easily. So this is an example from a textbook. So we want to figure out what the output is in terms of the input. So another way to say that is if we can solve for V naught, V output over Vs, figure out what goes on the other side of the equal sign here, we're done. We've solved this op-amp problem. All right, now let me show you how we can model this and use our knowledge of circuits to solve this. By the way, when we do that, we're not assuming ideal op-amp constraints. We're just trying to solve the circuit using analog techniques. So let me show you that. All right, now what we've done just here, right here, is we've modeled the op-amp that we see up here. So this is the internal resistance, that's the input resistance, and we said that that's a large value. Let's set it for 2 meg. So we've set it to a typical high input impedance here, high input resistance, and 2 meg is going to be its value. Now the output resistance over here is 50 ohms. All of that right there is inside of the op-amp. So I'll try to draw my little triangle here one more time. I'm going to run out of, it's not going to be a pretty triangle. But there's the triangle. All of that is inside the op-amp here. So we've got the 10 k ohm resistor that corresponds to that. There's the supply. I need to add the feedback resistor here. So we'll put that on right here, and that's 20 k ohm right there. All right, now every device that you see here is something that you've seen before, and you should be able to figure out what the output is in terms of the input pretty straightforwardly. Now the A is the open loop gain. Let's give that a typical value. So let's say A is equal to 200,000. Typical open loop gain. It falls within the range. All right, now we've got 2 nodes here. Let me see if I can mark those. So we've got a node right here. Let's call that node 1. And then we've got another node over here. We'll call that node 2. The voltage at this node over here is going to be V output. The voltage at this one over here, we can call it whatever we want. Let's just call it V1. I'll let that be the subscript for V1. Okay, so let's write a node voltage equation for V1. And when you do that calculation right there, that is approximately equal to -2. So in this case, what we've done is we figured out what the output is in terms of the input. So if we wanted to write it this way, V output is approximately equal to -2 V sub s. And notice it's inverted, so the output is inverted compared to the input, but we had to go through a lot of crap to get here. It's very tedious. What we've done here is the non-idealized case, and let's just say yuck. All right, so now let's work the same problem, but let's use our idealized OpAmp constraints and see if we can come up with the same answer. And the answer is yes, we will, but we're going to come to this as our conclusion without having to go through all of these squiggles on the page. So let me remind you what the circuit looks like. All right, very good. Now this was our 1 node and this was our 2 node. And let me remind you of the ideal OpAmp constraints, that VP equals VN and IP equals IN equals 0. So these are our ideal OpAmp constraints, and we're going to apply these right now. All right, by observation, you notice that VP, that's the voltage at the positive side, and this up here would be VN, voltage at the negative side, that VP goes straight to ground. So what does that tell you? That tells you that VP is 0. Then, if we apply the ideal OpAmp constraint, then that means that VN is also equal to 0. Okay, but we can still write a node voltage equation for node 1. So if we do that, what do we get? VN minus Vs over 10 k ohms plus Vn minus V output over 20 k ohms plus, okay, now what about this right here? Remember, the whole idea of applying node voltage method is you assume the currents are leaving the nodes. Okay, so this term here is the left current. This term here is the one going over the top. But what about this current going in? Well, that's Vn, and it's equal to 0. So we don't worry about it. Therefore, these are the only two terms, and it's equal to 0. Now with that, let's do what we normally do, find our common denominator and see if we can simplify things here. One of the first things I want to do, though, is just replace that with 0. So this becomes minus Vs over 10k minus V naught over 20k is equal to 0. So if I do V naught over Vs, let's put the V naught on the other side, and it becomes minus Vs over 10k. Now to keep it all on the same page, I'm going to scoot over here. And I'm going to divide by Vs and multiply by 20k. Then I got V naught over Vs equals minus 20k ohms over 10k ohms. The ohms will cancel, the k's will cancel. I've got 10, the zeros will cancel. I've got -2. So there, I just solved this circuit. That, by the way, is also called the closed loop gain, because V output is equal to -2 times V sub s, which was the input. So this is the amount of gain that you have for your output compared to your input. So, and we had a closed loop here with our feedback resistor, so that's why that is called the closed loop gain. The -2 is the closed loop gain, and we've just computed the closed loop gain. Okay, now let me ask you, which way was easier? I think it's kind of obvious. The way that uses the ideal OpAmp constraints is much easier, and that's the way we're going to do everything from now on. Now, I want to show you, in general, the method for solving any OpAmp circuit, because what we did here, in general, is the way that we're going to do it. First of all, we used our ideal op-amp constraints, that's right. But usually by inspection or through some mechanism, you have the ability to figure out one of these two. You will figure out either what V sub P is or V sub N is. And in this case, we figured out what V sub P was, and we knew it by inspection that it was going to be 0. Therefore, V sub N was going to be 0. So, first step, apply your op-amp constraints, determine which one of these you know, or which one you can figure out the easiest, and then set the other one equal to it. After that, write a node voltage method for either one of the inputs, and it should be obvious which one of the inputs you need to write the node voltage equation for. Okay, in this case, since V sub N went straight to ground, then we'll write a node voltage equation for this node up here. Okay, after you've written the node voltage equation, then you solve it in terms of the input. Now there is one last thing that we need to do, and that is check if there is saturation. Now in our problem here, we do not know the input voltages. But if we had known, let's say that this was plus 1 volt and this is minus 1 volt. Okay, now the output, if the input V sub S was 1 volt, so let's say V sub S is 1 volt, then 2 is going to be negative 2. That's outside the range here. So the output would be minus 1 volt in that case. All right. But if V sub S were, let's say, 0.25, then 0.25 times 2, that's going to be minus 0.5, and that's within the range. So that would be a good output. It would be in the linear range. Let's do another one, and let me show you that. Once again, this is going to be an inverting op-amp. Plus, minus, this is VP, this is VN. By observation, VP equals 0. Therefore, Vn also equals 0. Then, that's the first step. Figure out VP or Vn, applying those ideal op-amp constraints. Next thing is we can write a node voltage equation for this one right here. There. Now, because Vn is 0, we can go ahead and turn these to zeros. You guys hear that bird? So, what is the output? So, V output equals minus 6.67 volts. If you wrote that down, you would not be correct, because this is outside the range of plus or minus 5 volts. So the true output is going to be minus 5 volts. So it's saturated. So an input of 5 volts here is going to give you a saturated output, which means that you're going to be limited to 5 volts. Okay, so that's not necessarily a problem. If you're okay with that, just understand that this operational amplifier is going to saturate at this input voltage of 5 volts. All right, now other types of operational amplifiers exist, and we'll talk about some of those next time.
Hey, what's wrong with you? What happened to the legendary Man of Steel? I thought I knew.